This is the Mathematics Education Podcast from mathedpodcast.com.
Welcome to the Math Ed Podcast. I'm Erin Smith, a PhD student from the University of Missouri and a guest host for this episode. Joining me is Katy Ulrich, an assistant professor in the School of Education at Virginia Tech. Our conversation is going to focus on Katy's two-part article called Stages in Constructing and Coordinating Units Additively and Multiplicatively, published in 2015 and 2016 in the Journal for the Learning of Mathematics. And leading up to those articles, I first want to ask you, where did you do your graduate studies and with whom did you work with there?
I got my PhD from the University of Georgia in 2012, and I worked with Les Steffi.
So what got you interested in the topic of constructing and coordinating units?
So I was involved in a pilot study that Les Steffi was doing with 2 and sometimes 3 other graduate students. In it, we were just looking at well, it wasn't really a pilot study, it was an exploratory study at the time, although it didn't end up being my pilot study for my dissertation. We were really exploring how middle school students developed a bunch of different constructs. So he definitely looked at fractions, which is something he had already laid out pretty well. And then he was looking at combinatorial reasoning, he was looking at ideas of scaling up or scaling down, like ratio reasoning. And I wanted to throw in some integer addition and subtraction problems, which we did just for fun. And it turned out that one of the pairs had a horrible time with it, and that was very intriguing to me. Why would it be so hard to learn how to add and subtract integers and make sense of that? That got me interested in the idea of, if we say, we always were talking about multiplicative, or Les Steffi was always talking about multiplicative coordinations. Unit coordination always meant multiplicative unit coordinations. And I got interested in, well, what if students are making additive comparisons? How does that compare to making a multiplicative comparison? And that was sort of what I was looking into in my dissertation. So in trying to work out some of those questions, I got interested in the idea of just what are units and what does it mean to construct them and coordinate them. The other conversation that was really pivotal is I was talking to Pat Thompson at some point, and he was mentioning that he's starting to think that maybe it isn't multiplicative comparisons or multiplicative coordinations in general that are what makes something much harder for a student. So it's not that you're just adding another level that's multiplicatively related to the previous levels, but he thinks maybe it's just any quantitative relationship. So whenever you're having to keep track of multiple quantitative relationships, that is going to be hard. So if you're keeping track of 2 multiplicative relationships, that's going to be easier than keeping track of 3. And so that has really informed my later work and the end part of the FLM article, the second FLM article, because that's really what I was thinking about, just limiting myself to multiplicative and additive relationships. But, it turns out that, 3 is going to be harder than 2. But I think maybe what's surprising is that 3 levels of additive comparisons is harder than 2 levels of multiplicative comparisons. Mm-hmm. So that was something I wasn't necessarily expecting to happen.
So the articles came out in a 2-part.
Yes.
Did you always envision them as 2 parts, or was it always one article in your mind that you chose to split?
It was one article in my mind, but it got too long because FLM has a pretty strict word limit, which I'm not 5,000. I'm not really sure off the top of my head. But clearly what I had was way too long for that. And I didn't feel like there was a way to cut the article in half, without seriously changing the integrity of it. And I really wanted to lay all of these out together because we already have articles just on how they construct 1 level. And we have articles on 2 through 3. So I really wanted something that put those all together and talked about them at once. So I just wrote the whole thing out, and a couple of my colleagues read it, and someone said, I know it's way too long for FLM, but it just seems like the right voice, for FLM, because it was a little more conversational. So even though it was too long, I sent it in, and they were the ones that suggested it just be split up.
So in your articles, you present a framework that draws on a lot of research, as well as your own thinking about students' learning. How did this synthesis work come about? And was it always going to end up in the form that we see it in the articles? Or was there a different goal or a different format that you had in mind originally?
So originally, I was trying to write up a conceptual framework to explain how I was thinking about levels of units. There were several researchers at the time that were using, especially just in conversation, were using the terms levels of units or like a 2-level structure, a 3-level structure. But when I started looking around, I couldn't find too many places where some of those terms were really laid out. Amy Hackenberg had written about multiplicative concepts to sort of, I think, have an easier way of speaking about it. But she is really focusing on multiplicative comparisons like pretty explicitly. So I still was trying to figure out like what are units and what is a level of units and what does it mean to coordinate levels of units. And when I started trying to write it up, I basically realized that I had to first figure out what one level of units was. And that took me back to early work, in particular von Glossersfeld's JRME article that talks about the construction of units. And Piaget also wrote about the construction of arithmetic units. So just as part of my conceptual framework, I tried to tie that all together. But of course, after I had actually carried out the dissertation and thought about it for a couple of years, my understanding of the difference between an additive and multiplicative comparison and how that would play into it definitely deepened my understanding. So at that point, I wanted to get that out there for people to read more broadly. I also just have found it very useful in understanding the constraints that various learning researchers talk about in their articles. So they might not be talking about how many levels of units a student is working with, but when I was going through, I could sort of interpret their findings through that lens, and I found that useful to bring a lot of things together. So that was another reason I thought it could be useful for the broader community.
The idea for your article originally came out of your work for your dissertation, is that correct?
Yeah. And actually not even, it was before I had collected my data. It was just when I was trying to set out the conceptual framework I was using.
So since the time when you were working on your dissertation to now, how has your thinking about this topic changed and evolved as you wrote this out and have sent it out for publication?
I think the main thing is that I was conflating composite units with 2 levels of units for a while. And I think that constructing a composite unit is a little bit different than constructing a new level of units. And I don't think I fully appreciated that when I was first doing my research. The other thing is until I did my dissertation research and sort of analyzed the data, I didn't have an appreciation for how difficult additive comparisons would be. And so the idea of what would be involved in coordinating 2 different number sequences that are at the same level of units, that's fairly hard for students to do. And I think I underestimated that. So I think that even though I had this conceptual framework written out, I didn't have a good intuitive sense for how that actually played out in students' ability to carry out different types of problems. It wasn't until I did some follow-up research and specifically looked at the question of how does the difficulty of making additive comparisons or multiplicative comparisons compare, that I found out that as hypothesized, additive comparisons would be easier to make. However, what I didn't anticipate was that for many students, additive comparisons, if they don't have practice in working with additive comparisons, so differences basically, if they don't have practice with that, it can be quite difficult for them to work with additive comparisons. And so that definitely informed the end of the article where I'm trying to make links between additive and multiplicative thinking.
So before we go through the 4 stages of the framework, can you help us get on the same page about what a unit really is?
I can try. So, you could call lots of things units. We talk about, when students start counting, Steffi talks about countable units, countable unit items. So even when a student still needs objects in front of them to count, we will still sometimes use the term unit. However, when we're using the term unit in talking about levels of units or coordinating units, we generally mean an arithmetic unit. And so we mean something, it's an interiorized act of counting. And the way I like to think about it is that until the student really thinks about number as a quality of a set that can be measured in the units of counting by 1, until they have that concept of number, they don't really have a unit because there's nothing they're measuring. So when you see those younger students who are able to count but don't think of the final number as representing a quality of the set, what does it mean to call it a unit? They're not measuring anything. So that's the way I like to think about it, is sort of to connect it back to measurement. The other thing I can say is that I'm definitely building, as I said earlier, but I'm definitely building off the work of Piaget and von Glassersfeld and sort of theorizing and documenting how students develop units, interiorized units.
So can you tell us about the first stage of your framework?
Okay, so the first stage of the framework is basically the first stage at which we would say students are numerical, and that's going right back to what we were just talking about. So in the first stage, that's the first time that number is really something students see as a quality of the world. Like we think of just, we see the world in terms of color. Well, they see the world in terms of number. They develop that ability at this point. So at that point is the first time they really have units and one level of units, the way that we talk about it with middle school students. And some of the things that allows them to do would be to count on. So for teachers of young children, they'll recognize that that's a big step, is when students can learn to count on instead of count all. And for those of you that do secondary research, that means that if you give a student 8 marbles and then you give them another 5 marbles and ask them how many there are altogether, they don't have to recount those first 8. They can just say 8, and that will stand in for having counted the 8. And then they'll continue 9, 10, 11, 12, 13 as they count the other 5 marbles. So that's something that they're not able to do until that first stage of the framework. The other thing we talk about at that stage is that they have numerical composites, which means that they can experientially bound counting activity and count it. They're like aware of monitoring their own counting activity to some extent. However, if they're thinking about, like, they might know that counting 9, 10, 11, 12, 13 was 5 because they kept track of it on their hand or something like that. However, they're not really focusing on the 5 as one thing. They're still focusing in on each individual act of counting. So it's like if you think about foregrounding the forest or the trees, they're foregrounding the trees still at this point, which changes at the next stage. So those are probably the main characteristics of that first stage.
Okay. So taking us into the second stage then, can you say a bit about that?
Yeah, so the big thing in the second stage are composite units. So in the second stage, the students can construct composite units, and with younger students, that might sort of be the extent of it, but my work has mainly been with 6th grade students who obviously have been counting for a long time. And so by that time, they're really good at using their tool of composite units. And they've started using it in an anticipatory way, maybe even in what we would call an assimilatory way. In other words, I know they can anticipate the results of counting by composite units. So those would be numbers larger than 1. So they could count by 5s and anticipate the results of doing that activity. But I think it's possible that they even assimilate situations in terms of those composite units. For example, we gave out some problems where there were bars, and we said the first bar equals 5. And then the second bar was made up of partitions that were the same size as the first bar. So it was like, 4 iterations of the first bar. A student who can construct a composite unit, if we told them, like in the interview, if I were to say, well, what does it mean when I said that was 5? And then they were to say, oh, well, maybe that means there's 5 things in there, and they were to draw that out, then they could complete the problem. Mm-hmm. They had to construct that composite unit before they could finish up the problem. But for students that have been working with the TNS for a long time, they already are aware of the fact that when they see the 5, that means that there are 5 things represented by the bar. And so they can go ahead and form copies of that 5 and count 5 4 times to get 20. So that's something that my research sort of adds to some of the writings that Steffi has done in the past, because he was working with younger students for whom that second stage was pretty transitional. They would go through it pretty quickly. And I was working with students who had been stuck in that stage for I don't know how long, but if they were in 6th grade and they were still at that second stage, probably they had been stuck there for a long time. But regardless, everyone at the second stage can construct composite units. With younger students, a big change that you might see is that if you were asking them to find the difference between 2 numbers, like how many more would I add to 9 to get to 17 or something, they would understand that there is some amount between 9 and 17 that is a composite unit and that they could count it, and then they'll count off the subsequence from 10 to 17. At the first stage, students wouldn't spontaneously develop the ability to do that. You'd have to teach them that was the strategy to use. But by the time you get to 6th grade, everyone has already been taught how to do a lot of these things. So the big thing you'll see at 6th grade is that they're able to actually count by composite units, which basically is to make a multiplicative comparison. They can say there are 5 4s in 20, or they can say that there are 3 7s in 21, and figure that out by either skip counting or repeated addition or something like that, and keep track of counting by composite units. So that's why I would say that at that point they have constructed 2 levels of units, because they have their units of 1. We know they can count by that. And then they have their composite unit, and they can also count by that composite unit and measure off another number by that. So they can say, oh, there were 7 3s in 21. But with younger students, like when Steffi was working with K through 2 students, he did not see them usually able to do that unless it was a really small number, like a 2 or a 3 or something. So that was something that develops over time and is probably more indicative of the 3rd stage. Nonetheless, that would be an example of where at first I thought developing a composite unit meant you had 2 levels of units. But if you can't actually measure off another number by that composite unit, what does it mean to say it's a unit? You know, it's sort of, it gets a little bit complicated in that 2nd stage. The only other thing I'd say for the 2nd stage is, even though students don't understand fractions in a way that's at all similar to how you or I would, the advanced students can use their composite units as a partitioning template. So they can sometimes become pretty good at simultaneously partitioning continuous units into fractional parts. So if you said share this bar among 5 people, they could kind of picture the 5 and then mentally move it around to figure out approximately where to put the partition lines. And that's something that until that stage you really don't see students do that. They just can sort of equisegment before that stage.
So for our listeners, I'm speaking with Katy Ulrich from Virginia Tech about her articles in the Journal for the Learning of Mathematics. So to continue, can you tell us a bit about the 3rd stage of your framework?
Yeah, so the 3rd stage, you definitely can understand situations in terms of 2 levels of units. So not only can you construct composite units, but definitely at this point you can think about other numbers as made up of multiple copies of some other number. Like, you definitely know that 21 can be divided into smaller factors like 3s or 7s. So that's one really big change. You also, because that has become fairly clear to you at this point, you start to see students develop 3 levels of units, or 3-level structures, some people will call them. And so that would be when I keep saying that a student at the 2nd stage could tell you that there are 7 3s in 21, but they really are thinking about the act of counting by 3s 7 times. So they're really thinking about this counting act. So when you get to the 3rd stage, the student can actually think about 21 as made up of 7 3s or 3 7s. So they've reconceptualized their composite units to contain, after they constructed an activity, they can reconceptualize that containing larger unit like 21 as made up of the smaller ones, and as being in sort of a multiplicative relationship with the smaller ones. But that is something they have to sort of work out in activity. What that allows them to do, the big change you'll see here, is that students become fractional in the sense that they really can understand multiplicative relationships now. The previous stage, they could maybe come up with the answer you would want to a multiplicative question, but they don't really understand the relationship as multiplicative. They think of like repeated counting or addition. But at the 3rd stage, they actually think about things multiplicatively. So even like the number 8, instead of just thinking about, 8 means I've counted 8 times, so I've counted 8 members of the number sequence and gotten to 8, which is more what a 2nd stage student would think. At the 3rd stage, the student would say like, 8 would mean that I can take one of my counting acts and just do that 8 times. So they're thinking about 8 times as big as 1. So it's a whole new way of thinking about numbers. And one thing that allows is so like if we think about fractions, just even understanding fractional language, like 4/7, you have to understand that the 7 is representing a multiplicative relationship between the fractional whole and the fractional piece. So if I take that fractional piece of 1/7 and iterate it 7 times, I get the whole. And students just really can't do that until the third stage. So that's why we would call them fractional at that point. Another thing I talk about in the article is the ability for students to disembed reversibly. And usually people just say disembed and they mean reversibly disembed. But that would mean they could take out some, maybe the difference between 12 and 19. They could take it out and operate on it. Maybe they change 19 to 20 and figure that out. And they know that's 8. But then they can go back, put it back in the original sequence and say, oh, but I need to decrease 20 to 19. So they can do a lot of strategic reasoning with addition and subtraction. And with fractions as well, there's sort of the sense that, whenever you're making a multiplicative comparison, you have to be able to think of the two quantities as separate from each other and then think about measuring one of the quantities off by the other. Whereas before the students they were always operating within a larger number.
So now can you tell us about the fourth stage, the final stage?
Yeah, so in the fourth stage, this is sort of the pinnacle. This is when students can coordinate, we say they can coordinate 3 levels of units, but basically it means that they can keep recursively doing this process. And so, you can unpack sort of anything at this point. You can unpack 10,000 and unpack that into thousands and hundreds and tens and ones and all of that kind of thing. So you can understand multiple different multiplicative comparisons. But importantly, you can consider more than one of those multiplicative comparisons at a time. So you can actually consider 2 at a time. And what that means is that for a student at that stage, they could conceive of 4/7, for example, as 4 times as big as 1/7, which is 7 times smaller than 1. And they have that all of those implications are in their head at once. So that would be true for you and I. And for fractions less than 1, it turns out that that's not such a big deal to be able to keep track of both at once. But for improper fractions, research has kind of shown that that's a serious constraint. If students can't understand 9/4 is 9 times as big as 1/4, which is 4 times smaller than the fractional whole. If they can't understand the 9 and the 4 as representing multiplicative relationships, it becomes hard to really operate or even understand what's going on in 9/4. Before that, so at the third stage, when they're thinking about a fraction like 4/7, the 7 represents a multiplicative relationship, but the 4 is more just you have 4 of those 7s, more like a counting kind of thing. You have 4 of these 7ths. Whereas at the next stage, if they're thinking about 4/7, it's 4 times as big as 1/7. So then it makes sense to say you have 9/7, because clearly you can just iterate 7ths 9 times. Before that, it wouldn't make a lot of sense because you're still, at the third stage, they're still thinking about just that multiplicative relationship between the piece and the whole. And so let's say that multiplicative relationship is 7 for 7ths. So if they're thinking about 4/7, then they're counting 4 of those 7 pieces. And if you try to tell them 9/7, then they're like, no, there's only 7 pieces. You don't have 2 more that you can magically grab. So at the fourth stage is really when they can work with improper fractions. And the big implication for middle school is that's when they can conceptually understand a lot of the things that we expect all students to do at middle school. So a lot of the operations on rational numbers, especially if you're going to throw improper fractions in, you need to be able to understand improper fractions in that way to make sense of what's going on with the algorithms. And, I would say that we know most students aren't there by 6th grade, so that means that a lot of students are just kind of memorizing these algorithms before then. It also gives them a good place to start from when they're getting to algebraic reasoning in an algebra class, because in algebra a lot of times you're asked to think about a multiplicative relationship between an unknown and some other number, and that can be hard for students to do until they have that ability to think about multiple multiplicative relationships at once. So if you said 4/7 times x equals 3, it just doesn't make sense to a student until they get to that fourth stage. So we think of the fourth stage as being the final stage, not in that once they've constructed the operations underlying the fourth stage, they're done, but more just that they have learned to deal with high levels of mathematical complexity at once, and we think they can continue to reorganize their different mathematical conceptions to deal with sort of any level of complexity thrown at them, at least for the rest of secondary mathematics. So the fourth stage is sort of sufficient. Some people say that they think that people only, the most we can coordinate once is 3 levels of units. Sort of the same way that I think Husserl said that we can't picture more than 12 items really at once in our mind. And for some people it would be less than that. But I have wondered sometimes when I work with mathematicians, that are really dealing with super abstract structures, if in order to do that they don't need to, if there isn't some other stage that we don't even bother studying with middle school students, So that's sort of an open question.
How do you hope to see this framework being used in research and in practice?
So for research, like I said, I find it really useful for bringing together a lot of the research that is being done on student learning in the middle grades in particular. I'm sure it would be useful with the elementary research as well, but since my research is in the middle grades, that's what I've been attending to. Because lots of researchers find constraints they come up against when they're trying to do some kind of an intervention, or they'll note that one type of problem seems to be much harder for students than another type of problem. And a lot of times when I'm reading through those, I can understand that in terms of this framework, and it makes sense to me, and I can kind of drop it in and say, oh, that helps me understand why this difficulty would be there, and also whether I think it's teachable or not. In other words, if you have a student who's at the third stage and you need them to do a problem where they're considering 2 multiplicative relationships simultaneously, that just might not be within their zone of potential development or construction, at least not without figurative material or some kind of support available. So that gets into the implications for practice, but basically as a teacher, I feel like if teachers can generally understand some of these stages, and at any given grade level, it's not as important to understand the first stage when you're teaching 6th grade. You will have some of them, but you're dealing with so much complexity by 6th grade mathematics that basically you're going to have to scaffold the first and second stage quite a bit, so you can kind of treat them, similarly. But whichever grade you're teaching, there's going to probably be 2 or 3 stages you really need to sort of understand the types of constraints and affordances the students will have at those stages. And that will help you understand whether you should keep students to metacognitively reflect on a problem, or whether you really just need to allow them to draw part of it or show them ways they can use manipulatives or diagrams or something to scaffold their thinking, because you'll understand, oh, they can't keep track of that much complexity in their head, so I need to help them break it down, Whereas you don't want to do that with a student at the 4th stage, because they're ready to sort of blossom. You want them, they're more mathematically powerful than that. So you want to push them to not write things down, or to maybe even do an extension where they're using an even harder quantity to reason with. So I feel like it can be used to help teachers differentiate their instruction quite a bit. That's something, even when I'm working with the elementary pre-service teachers, sometimes we'll talk a little bit about that. What would you do if you had a student who you thought had a part-whole conception and wasn't able to develop partitive conceptions? In other words, what if you had a student who was at one of the first 2 stages, but you have to do fractions, actual fraction problems? So we talk about ways you can scaffold that complexity for them.
So where do you see your research going next after this work that you've done with the framework?
What I would like to do is to get a handle on what the approximate percentages are for students at these different stages. And I'm obviously interested in 6th grade because that's who I usually work with, but certainly other grades as well would be interesting. And so right now I'm trying to develop a written assessment that would approximate the analysis I could do in a clinical interview of where a student is as far as their stage, and then scale it up so that I can look at multiple classrooms. So I'm on the 2nd iteration of that right now with one of my colleagues, Jay Wilkins. And that's been really interesting. And I think, once we have that data, then that can help inform instructional recommendations or policy recommendations and that sort of thing. But at the moment, until we really have the data to say, most students at 6th grade are not fractional, and yet you're having them do a bunch of operations on rational numbers. Unless we can really say that that's true, our recommendations don't hold as much weight with instructors. So, and then the other thing is figuring out, I guess there's a couple things. One is figuring out what are the instructional implications of some of this. I'm just starting to think about that now. So especially with some of the topics that are in the middle grade, some of the mathematical topics there, what are the implications? In my dissertation, I teased out some of it for integers, but it was just integer addition and subtraction. So, multiplication and division still out there. Amy Hackenberg and others have done some work going toward how do some of these ideas link to algebraic reasoning, but there's obviously still work to be done there. So definitely just thinking about what implications does this framework have for various mathematical contexts, and then how you would need to support students in the different stages when they're in these different contexts is a big thing. And I would also be interested in going back. This will be a decade, 2 decades down. But I would definitely be interested at some point in going back and looking at some of the contexts in the elementary grades that haven't been explicitly linked to this. So some of the geometric concepts, understanding angle or something like, Kevin Morta's work on angle measure. Well, how does that all relate to what we're talking about here? How does angle as a quantity compared to dealing with, counting as a quantity or fraction as a quantity? And also statistics and probability is another place. We don't really understand exactly what it means to have a statistical variable, so to speak, we're not sure how that relates to all of these different stages. What does that mean a student can do as far as understanding probability as a quantity? So there's lots of work that could be done, and I think it's just going to be, I like working with other people. So right now I'm working with someone who does quantitative research and has done written instruments before. So I was like, hey, that's a good idea. Let's do that. So I think there's a lot of directions to go, and it's going to depend on, what are my colleagues' sort of interests and who can I work well with and develop a good working relationship with.
So we have one final question. If you were not working in mathematics education as a career, what can you imagine yourself doing instead?
So Erin and I were talking about this question before the podcast started. And we both were thinking about what do we do? What do we do in our time outside of the job, and what are sort of our interests? And, some of those do not translate well into careers. Like, I don't think I'd really become a professional dog walker, but obviously I spend a lot of time walking dogs. I have 2 dogs. But I think probably it would be, if I were going to go back and study something else, I think it would probably be religious studies, because I've always done a ton of reading on different religions, and I'll look at, the different hermeneutical techniques that religious scholars use. And I'm just really interested in the sort of academic side of that. So I think that might be, if I had to go back and, the mathematics education world exploded or something, and I had to go back and tell Katy, 20 years ago what to do, maybe that would be the best thing.
Do you think you would still go into academia? Or would you take that in a different direction?
I know. So, yeah, I guess I probably would stay in academia for that. And so knowing what I know now, maybe I would walk dogs. Maybe. Thank goodness there's math education. Right. Let's just say that.
Well, Katy, thank you for taking the time to speak with us about your work. This is Erin Smith for the Math Ed Podcast. Sam will be back for the next episode.